Hello, in this video we will be looking at sequences. A sequence of terms A1, A2, A3, etc. is a list of elements written in some specific order. So the first term is A1, the second term is A2, etc. They are normally denoted by the notation curly brackets A subscript n or just A subscript n, where an represents the nth term of the sequence. Now a sequence could be finite if it has a finite number of terms. For example, if it stops at say the 100th term or the 500th term, or it can be infinite if it just goes on forever. In this course, we will be looking at or focusing on infinite sequences. Alright, so first I have a couple of examples of some sequences. So the set of positive integers is an infinite sequence. Right, so the first term is 1, second term is 2, etc. The general term of the sequence would be an equal to n, right? Because the n represents the value of the nth term. You can also have a sequence of odd positive integers. So 1, 3, 5, 7, 9, etc. Here the general term is an is equal to 2n minus 1. Right, where n is a positive integer. We can have the sequence of perfect squares, 1, 4, 9, 16, etc. Again, here an is equal to n squared, where n is a positive integer. Alright, now you'll notice I'm talking about functions here after I talk about the sequences. So this function, if I consider the function f of n equal to n. Now, when we talk about a function, normally the domain of the functions that we're talking about are a set of real numbers. So when I say the function f of n is equal to n, normally in this course you would say, well, okay, n is a real number. In this case, this sequence, on the other hand, n is not a real number. N is an integer, or positive integer to be more specific. Now the function f of n is equal to n is said to generate this sequence, right? Because if we take the general function f of n equal to n, where n could be a real number, and replace n with a positive integer, then that will give me the terms of the sequence. Right? The function itself provides values for much more values in the domain, but we are only concerned with these which it generates. Right? Similarly, if I wanted a function to generate this sequence, I would say, well, f of n is equal to 2n minus 1, etc. Here we have another example, the harmonic sequence, basically 1 over n. Again, this sequence is generated by the function 1 over n. We have the arithmetic sequence, the geometric sequence. I'm not going to talk too much about these. You all can look at them yourselves. Alright, so we are going to, in this course, we're going to be looking to find the limit of an infinite sequence. Or in other words, we want to know what happens with the terms of the sequence as we get larger and larger values of n. Meaning, as we go further and further into the sequence, what happens? Do the terms of the sequence converge to a number? Do they get closer and closer to a number? Or do they just do any random thing? Do they diverge? So that's what we want to find out. Right now, important thing to bear in mind when we are talking about the limit of a sequence. Before in this course, all the properties and theorems and stuff we discussed were with respect to real numbers. Basically, the function took on the entire set of, the domain was the set of real numbers. But here for a sequence, you have to be a little careful about this, because for a sequence, the domain isn't the set of real numbers, as we just discussed above. The domain is really the set of integers, right? Because n, the value that we substitute in, are integers. The n value is an integer value. And that we call a discrete quantity. Right? Discrete quantity meaning it can only take discrete values. There's a jump from one value to the next. So from 1 to 2, there's a jump. On the other hand, before, all the properties and stuff we discussed with respect to limits were over continuous, or for continuous functions, where the domain was the entire set of real numbers and there wasn't a jump from one value to the next. There's a sort of smooth movement from one point to the next to the next. Right? So when we're talking about finding the limit of a sequence, we will have to first take the sequence. All right, so let me look at this example. We'll take the sequence, look at the function that generates the sequence, and then find the limit of that function over the set of real numbers. And important thing here, we need to convert the domain to the set of real numbers, find the limit using the properties and theorems we discussed before, which were applicable to real numbers, and then that will give us the limit over the set of real numbers. And then we're going to use this theorem. All right, forgive the notation here. We'll use this theorem to actually conclude what the limit is. So what this theorem says is we have n is a positive integer. Let that represent the general term of an infinite sequence, and let f of n be an be the function that generates or produces the same sequence. So basically f is a function that if n were an integer, we will get the terms of the sequence. Now what we're going to do is change the domain of f. Rather than integers, we're going to change it to positive real to real. All right, the domain is positive real numbers this time. All right, and then when we plug in a positive real number in there, we'll get some real number. So this is going to be defined over all positive real numbers. So x could take any positive real value. It doesn't have to be an integer value. And we're going to consider the limit of f of x as x goes to infinity. Now the reason why we took positive real numbers here is because as x approaches infinity, we don't really care about the negative values, because x isn't really going to go through those values. To get to infinity, it has to go through a lot of positive values. Alright, so now this is what the theorem says. The theorem says if the limit of f of x as x approaches infinity, where x is going through real numbers, if this limit is L, then the limit of the sequence as n approaches infinity through integers, that limit is also L. Alright, so this theorem is very important. This is what is going to allow us to work out the limit of an infinite sequence using the properties that we discussed before. Alright, so if I ask you to find the limit of an infinite sequence, I would expect you to go through these 4 steps. First, we define the function f. So we let f of n be the same as the function that produces the sequence. Essentially what this means is you let f of n be equal to whatever an is. And then the second step is, well, we change the domain of the function f. Rather than integers, we change the domain to positive real numbers. The third step is to find the limit of this function f over, well, as x approaches infinity through positive real numbers. So this step here is basically where we find the limit, as we would have done previously in this course. This step is the main part of this, of any question that you get on this, and this is where a lot of your work goes into. But it's important that you set it up beforehand. Right, now once in step 3, once you find your limit, then we use this theorem that I just mentioned and conclude that, well, okay, if the limit of this thing is L, then this limit is also L. Alright, so let's look at some examples here. So find the limit of the following sequence as n goes to infinity. So this here is the harmonic sequence. An is equal to 1 over n. So to do this, formally, what you need to do is, well, not formally, but if you want to actually write up a proper solution for this based on what we've discussed in this course so far, you need to introduce a function f, let f of n be whatever an is. So f of n is equal to 1 over n. And then you consider the function f over a new domain. So you consider f of x is equal to 1 over x, where x is a positive real number. Right, so here n is positive integer. You replace n with x and let x be positive real number. Once you do that, then you find a limit of this f of x. So you find a limit of f of x as x approaches infinity. Remember, it's the limit of the sequences we get further and further in. So we're looking as x gets bigger and bigger and goes to infinity. Alright, so here we would just replace f of x with what we know it is. It's just 1 over x. And remember, at this point, we can go back and say, well, we know that, or from what we've discussed in class, that the limit of 1 over x as x approaches infinity is 0. So this limit of f of x is 0. Alright, therefore over positive real numbers as x approaches infinity, 1 over x, which is this thing here, goes to 0. And hence over positive integers, as n approaches infinity, if n is a positive integer, then 1 over n will also approach 0. And therefore we conclude that the limit as n goes to infinity of an is just 0. Alright, now important definition here. So if we are able to find the limit, if it exists, then the sequence is said to be convergent and it converges to that value. If we cannot find that value, meaning if it's undefined or if it is plus or minus infinity, then the sequence is said to be divergent. Alright, so the example we just saw, the sequence is convergent and it converges to 0. What this means is that as n gets bigger and bigger, the terms of the sequence gets closer and closer to 0. So when n is a million, 1 over a million is a very small number, and as n gets bigger, it gets closer and closer to 0. Alright, so let's look at an example of something that you might actually see in a question you have to do. So determine if the following sequence is convergent, and if so, establish what it converges to. So we have an is equal to 2n plus 1 over n plus 3, n is a positive integer. Alright, so you'll notice that I actually skipped the first step here. Alright, so let me go back up here. So define f of n as a function that produces sequence. So these two you can actually combine, which is what I did there. Rather than saying, well, f of n is equal to whatever it is, you could just say, well, just replace n one time. So we automatically get f of x. Alright, so we let f of x be this thing, but we replace n with x. Right, and remember, if you're going to use the properties from before, this has to be defined over positive real numbers, not just positive integers. So we let f of x be this expression where f is defined for all positive real numbers. Or another way to say this is you let f of x be this where x belongs to the set of positive real numbers. And we consider the limit as x goes to infinity of f of x. So the limit of this. Now remember, when x goes to infinity, plus or minus infinity, when we have a fraction like this, we'll take the denominator, find the highest power of x, and divide everything everywhere by that power of x. So we divide everything by x in this case, and 1 over x, 3 over x will both go to 0 as x goes to infinity. So the answer is just 2 over 1, which is 2. Right? So how I have written this here is how I would expect you to give me a solution to a question like this. You introduce f, where this x belongs to a set of positive real numbers. Then you find a limit as x goes to infinity of this using properties from before. Then you need to conclude, well, remember, we're not trying to find the limit of this, right? We're trying to find the limit of an. So we'd say, well, therefore, the limit as n goes to infinity of an is just 2, right? As the limit of this, which is 2. So the sequence is convergent and it converges to 2. That's another important thing I want to point out here. This question is actually two parts. First, determine if the sequence is convergent. Second, if it's convergent, tell me what it converges to. So you actually have to give me two answers. You have to say, so the sequence is convergent, yes, and it converges to 2. So make sure you answer both questions. If it isn't convergent, well, then you just say it's divergent and you stop there. Alright, so we have one other question here. I'm going to just skip through this quickly. So again, we introduce f of x, replace n with x, call that the function, where x is a positive real number. We find the limit as x goes to infinity of this. Alright, so we divide everywhere by square root of x, simplify it. Now when we do that, 1 over x goes to 0, 5 over root x goes to 0, but this 3 root x on top, as x goes to infinity, this will go to infinity. So the limit is actually infinity, so it doesn't exist. All right, that's important to remember. And since the limit doesn't exist, it means the limit of an actually is infinity, so that doesn't exist. All right, remember these two are supposed to be equal. So this limit doesn't exist, which means that the sequence is divergent. All right, last example here. Well, actually, there are two more. So I'm gonna skip this one here. This is straightforward again. Same. This time you divide throughout by x squared after you introduce your function f of x and take the limit. And here the limit works out to be 0. So therefore, this limit is also 0. And hence the sequence is convergent and it converges to 0. Right? There are two examples here. So determine if this sequence is convergent, and if so, establish what it converges to. So we have an is sine of n over n. So again, we let f of x be sine of x over x. And we want the limit as x goes to infinity of sine of x over x. Alright, now this is actually a question that you would have seen in your assignment already. But the answer here is 0. This limit is 0. It is not 1. Alright, as x goes to infinity. Sine x is bounded between minus 1 and 1. And so you have something on top that is between minus 1 and 1, but the denominator goes to infinity. So something finite over something infinite is 0. Hence, the limit of an as n goes to infinity through integers, this is also 0, and therefore the sequence is convergent and converges to 0. Alright, now sine of n, if an is sine of n, remember the limit as x goes to infinity through positive real numbers. This limit of sine of x is undefined. It doesn't exist. Right? So therefore the limit of an doesn't exist, so the sequence is divergent. Now divergent doesn't always mean it goes to infinity. Divergent just means it doesn't converge. Right? So in this case, it doesn't go to infinity, but it's still divergent because it doesn't converge to a value. Right, here we have a definition for monotonically increasing, strictly increasing, monotonically decreasing, and strictly decreasing. I'll leave this for you all to go through yourselves. Alright, so I'm going to stop this video here because that is pretty much what we need to cover for sequences.